Hey, today we're going to be talking about what's called the general solutions, and this specifically does mean something important, general solutions, to trigonometric equations. Like I said, the goal on your paper is incorrect, but we're going to consider and write solutions to equations over the entire set of real numbers. So this example right here actually helps us set up the situation. So the function y equals the tangent of 2x is graphed here. So all of these, sort of like raindrop function, is graphed here. And when you graph y equals 3, it's a horizontal line that crosses here. And then, of course, your solution is just going to be all the points of intersection. So here are your solutions. Now, interpreting that solution is something different. So what we have to do is drop down to find out what the x approximate value is, or the x's. So what are the values of x in radians that make 3 of the tangent of 2x true? And forgive the grammatical mistake there. All right, so let's just focus in on the first one that I can see. This one right here is slightly past the negative, or shy of the -1. Right? So if I were to drop it down, it would be right here. And I would argue that it's somewhere around negative 0.9, maybe even closer to 9.2 or 9.3. Next, I have this one right here, which is slightly above. 1 is here, so this is slightly above 1/2. So, and forgive me, I made a mistake. It's got to be negative on the first one. Next, so if I had to say 0.5, maybe 0.6, etc. And then this one here is slightly above the 2, but it looks like it's even beyond slight. So here would be 2.25. So if I had to argue, it would be maybe 2.15, something like that. And of course, we can keep going. So every single one of these requires me to do an inverse. Because I have the answer, I need to find out what the question is. So I have to estimate each one of these. And notice that it goes on forever. Because the tangent has no restrictions on its domain. The tangent doesn't. Which means when I'm considering what makes this true, y equals 3, every single one of these is true. Every single one of these. As opposed to the restricted tangent inverse, when we're just focusing on this section right here. All right, so this sets us up to show us that we have sort of an infinite number of solutions. And notice it's evenly spaced here. So it's evenly spaced backwards and forwards. So today we're going to look at that as we solve trigonometric functions. Not only are we going to solve within the standard domain, like in this region, but we're also going to extend it beyond to find out all the solutions. And hence the title today, the general solutions. It means all the solutions by adding that specific amount every single time. So let's take a gander here. We're going to solve the simplest trigonometric equations. So notice how simple it is. It's simply just an inverse. I need to undo that cosine. So let's walk through the steps that we're going to effectively do. Number 1, we're going to use our calculator to find the inverse because the calculator inverse function has its domain set, right? So I can find the domain between 0 and pi. By the way, since I see the pi, I can safely assume I'm using radians. If it said 0 all the way to 180 degrees, then in that case you would say degrees. So because of the restriction on the domain there, I know I'm going to be using radians. So we're going to use the inverse to solve that. So effectively what we're doing, cosine of theta is equal to 0.6. So I'm just going to take the inverse of the cosine of both sides. like so. Notice when I plug that into my calculator, beware of this. The first time I plugged it in, I noticed I got 53, which would be odd to have 53 radians. In that case, that would be looping around the circle a couple times because it's only 6.28 radians around a circle, right? So that's way too large. Hence, I had to go back into mode and change that. So when I do punch it into my calculator, I get slightly less than 1 radian here. So there is 1. So theta is approximately 0.927. It asked me to round it to the nearest thousandths. Okay. Now, because of the nature of its cyclicalness, I'm sure that's not even a word, we're going to subtract it from 2 pi, kind of like supplementing, but it's 2 pi instead of 1 pi. So what we do is subtract 2 pi and then subtract the answer from that. So I'll explain it in a moment to see why we do that, but I get the 5.356 there. 5.356. So why did I subtract the 2 pi? Well, the nature of it is extremely helpful when we see the graph. So let's pull up a calculator. And I'm going to graph the cosine of x. And I'm also going to graph y equals 0.6. And this is just like we did in our warm-up. So notice what we get here. I see that there's one solution right there. In fact, there's another solution reflected over there, which we'll get to in a moment, so I won't consider that now. And we also have this solution right here. But remember our restriction on what we were just said. The first restriction we had was on between 0 and going up to pi. And pi is 3.14, so it's roughly here. So notice the 0.92 falls in that region. Next, all the way up to 2 pi, which brings me to here. So that's my 2 pi radians. Here's my pi right there. So now notice, because of that, this first one is the 0.97. And then my second one is over here, the 5.356, which is right there. So what did I do? I subtracted that from the 2 pi. Because remember, this is cyclical. Every 2 pi, it repeats the entire process. And because of that, because of every 2 pi, it repeats. Notice that one solution is this. Then another solution is you add 2 pi to it to get to the next cycle. And then you add another 2 pi to it to get to the next one. So notice what I keep doing. I keep adding a 2 pi to it, but I'm multiplying each one by another factor. So notice the next one is going to be here, but I'm going to now say 6 pi added. So what we're going to do, and this part right here is called the general solution, is instead of writing it out and there's going to be an infinite number, notice all we're doing is taking 2 pi and just multiplying it by 1, 2 pi multiplying by 2, 2 pi multiplying by 3. So notice there's a pattern. So how do we write that? It's actually as simple as this. I found my first term right there. So to find the general solution, I just say it's 2 pi times n, and n being whole numbers. In fact, they can also be negative, so n has to be an integer, which I'll put that over here, plus 2 pi n, where n is an integer. And the same thing applies over here. I just find my second theta, and I just add 2 pi n to it. So when we commit to the answers, these are my two general solutions. First one was a calculator. Then we subtract it from 2 pi, so the calculator of inverse. Subtract from 2 pi in order to find its partner in the same cycle. And then we just added this generic term to show that it repeats every 2 pi. Or if we go in degrees, every 360 degrees, we come back to the solution. By the way, n can be negative, a negative integer, which means we're going backwards, or on my graph, we're going to the left, which we see as a reasonable situation. So check your work on this one here. We do have to take the inverse of sine for both sides here. And of course, this will restrict it just to an acute angle, most likely. So when we punch that in our calculator, we get approximately 0.443. So we have to now, and notice I'm calling that one theta 1 because I have more than one option. Now theta 2 just simply says I'm going to subtract that from 2 pi. 5.840. All right, so now we need to generalize it by adding the cyclical part, the 2 pi n for each of these. So these are my two solutions in radians, just slightly under half, and slightly under 6 radians here.